Now, I want to go back just briefly. So we were talking about PLC hardware, and I showed this kind of a generic picture of a typical PLC, and we identified some of the sections of the PLC. There's an input-output section that's important, and we discussed a little bit about that in the last class. We'll talk a little bit more about that this class. We talked about this section of the PLC, the controller. We also call that the CPU. And then we didn't really talk specifically about power supplies, but in our diagrams and pictures, we did show the power supply. So what I want to do today is a couple things. I want to delve into a little bit deeper the I/O section and talk about two different types of modules that you can have. But before we do that, towards the end of the last class, we talked about the CPU. There was a PowerPoint. We talked about the CPU. So let me just kind of go back to that real quick, because I went through it kind of quickly because I was running out of time. So I'm just going to kind of just click through this real fast. I want to make sure that the important points that you guys are able to identify the important points that have to do with the CPU, and then we'll move on with the lecture. We should be done early today. I mean, the other PowerPoint is pretty short. So we talked about the central processing unit in the original diagram that I showed you. They refer to this as the controller. The three main parts of the CPU: there's a power supply for the CPU. There is a processor that's also called a microprocessor. And then there's memory. I haven't said a whole lot about memory, but I want to point you to some documents that's on your Canvas. I'm not going to talk about those documents, but make sure you click through your week 2 material. There's a couple papers, couple handouts, couple documents that I won't talk about. However, you're still responsible for the information on those documents, and one of those has to do with types of memory. So just kind of briefly, when you deal with digital devices, when you deal with computers and cell phones and those type of devices, there's two types of memory you can have. One is called RAM, R-A-M, RAM, and the other is called ROM, R-O-M, ROM. RAM stands for Random Access Memory, and ROM stands for Read-Only Memory. And I don't want to go too much into details about them, but I'll say just a little bit about the memory, the difference between RAM and ROM. First, let me say that all memory is random access. No matter what type of memory we're talking about, all memory is random access. It didn't used to be that way. Years ago, before solid state memory, we would record those ones and zeros on either magnetically or on tape. I mentioned when we talked about the digital advantage, I think I gave an example of recording on cassette tape. Well, they actually used to store computer information, binary, machine language on tape. And as the tape moved past the tape head, it would record information on that tape head that would represent a binary 0 or binary 1. You would record data that way. If you want to get the information back, you had to kind of wind the tape or roll the tape the other way, and you're actually moving those bits in single file, bit by bit. So if you had something at the end of the tape that you needed to go to, the computer had to rewind the tape all the way to the end to grab the data that it needed, and then go back to another spot maybe to move data around or to store data. That is not random access. Random access means that you can access all parts of memory in equal time. So if you heard the term, maybe you bought a computer, you look at the spec sheet, they talk about how much RAM you have. Random access means you can access all parts of memory in equal time. So all modern day memory is random access. The difference between random access, RAM, or ROM, which they don't use the word random, but ROM is still random access, is that RAM is volatile memory, ROM is non-volatile memory. And remember we talked about the meaning of the term volatile and the meaning of the term non-volatile. If it's volatile, that means in order to store the information, you have to have power applied to the memory. So I think I gave as an example, if you're typing a letter in Word, or if you're using an Excel, using any document on your PC, or you're using maybe an app on your phone, and you need to store data, if you don't hit the save button, if that information, if that letter, that document, that Excel spreadsheet, if it's in RAM and you unplug the computer, then you lose it. Everything's erased. If you want to save it, you got to move it to a hard drive or some kind of maybe solid state memory. So once you move it to a hard drive, which that's a little different than memory. You have memory, which is for short-term use, and then you have storage. A hard drive is really storage, but I'm kind of using the term as if they're the same. But the point is, RAM, if you have information, you have data in RAM, if you remove power from it, that information, those zeros and ones, they're erased, they're gone. Whereas ROM is non-volatile, which means it's gonna store the content whether it has power or not. Now, typically ROM devices, ROM chips, ROM memory, that type of memory is usually pre-programmed at the factory. The reason we use ROM is, if you remember when we talked about, in the last class, I briefly talked about the OS, the operating system. Think of the operating system as the layer between the application software that you're using and the actual hardware. I put a diagram on the board in the last class. I'm not going to go into it now, but you can look at that video. You're the user, and you're interacting with the computer through some kind of application, using Word. On your cell phone, you're using, well, I don't have a cell phone. I don't know what kind of app you're using, but you're using some kind of app on your phone. You're interacting with that app, and that app is interacting with the operating system. And so that operating system, before you turn the computer on, before you turn your cell phone on, that operating system has to live somewhere. Well, where does it live? It can't live in memory, because memory needs power. Memory is volatile. The operating system lives on the hard drive inside your cell phone. You might not think about it like this, but inside your cell phone, there's circuitry. There's a solid state hard drive, and the operating system, the OS of your cell phone, lives on that hard drive. Well, when you turn it on, you have to have enough smarts. Your device has to have enough intelligence to bring the operating system up and load it into RAM. And so the only way to do that is to already have some kind of instructions stored, the instructions on how to boot the system up and move the operating system from the hard drive to RAM so you can use it. The microprocessors uses RAM directly. So whatever you want the microprocessor to operate on, you got to have that in RAM. So you turn the cell phone on, you turn the computer on. The way it knows how to boots up is a small program in ROM, which doesn't need any power to store those instructions, to give the machine, the device, enough instructions to bring the operating system up to RAM. And now you got a computer, now you got a cell phone, or whatever digital device you're using. So two different types of memory. In here, when we talk about sizing memory, when you talk about sizing memory, 99 times out of 100, you're referring to ROM, random access memory. If you have a computer, I had one of your colleagues asked, we talked about the clock, when we talking about digital clocking, the clock circuit, and after class he said, well, when they overclock a computer, is this what they're talking about? That's exactly what they're talking about. So typically, when you hear memory or you talk about memory, 99 times out of 100, you're talking about RAM. If you want to upgrade memory, you're upgrading RAM, and that gives the microprocessor more ability to interact with greater data, and it can do it often. It can do it faster. So RAM and ROM are important. So we went through this, and again, I don't want to spend too much time on it, but there is one slide I want to make sure. So right here it says memory is where the control plane or program is stored in the PLC. The information stored in memory relates to how input and output data should be processed. In other words, when you write your program, and you will write a program in this class, if you had other programming languages, you use a language that we in computer science call a high-level language, meaning I don't know what you guys take, most of you mechanicals. You might have, I know when I was in school, I took Fortran, Basic, C, I know several computer languages I took when I was in school. You guys, I think you may do something with Mathematica or something. You use some kind of programming language. Those are all, any programming language where you use high-level English words like print or format, anything like that. Those type of languages are what we refer to as high-level languages. Well, the language we're going to use to program the PLC is a graphical language. The instructions are not words, they're actually symbols that represent something, and they're actually symbols that represent relay contacts. And so when you write your program, and I mentioned before that program is called a ladder, when you write that program, well, that program has to be stored somewhere. That program is going to be stored in memory. So the way it's going to work is you'll enter the program into some kind of programming device. Well, that device itself, it has RAM, it has memory. You'll put your program in that programming device, you'll edit it, and you'll do everything you need to do. When you're ready to run it, you'll move your program from the programming device down to the PLC. At that point, this memory that I'm referring to on the PowerPoint, that's the memory I'm referring to where your program is going to live. And so some terms that have to do with memory, and I think in the last class, this is kind of where I started to speed up a little bit. So I want to make sure you're clear on these. Make sure you have if you printed your PowerPoints out like I asked you to, here's where you want to write some notes. This will be asked about at some point on an exam or quiz. You want to make sure you know what a bit is. What is a bit? A bit is short for binary digit. A bit is a 1 or a 0. It's the smallest piece of digital information you can have. Then we move to bytes. A byte is a group of 8 bits. A byte is a group of 8 bits. There's actually another term I don't have on here called a nibble. A nibble, like a fish might nibble at the bait. A nibble is 4 bits, but we usually think in terms of bytes. So a bit is a 1 or a 0. A byte is a group of 8 bits. And then there's where the confusion can come in is when we use the word kilo, because you guys are all engineering students. And when you think kilo, you think, all right, that's 10 to the third, that's 1,000. Well, it depends on what we're talking about. If we're talking about kilobits, then yeah, it's 1,000. If we're talking kilobytes, it's something else. So if you notice on the PowerPoint, I have a KB, and then I have KB again, but the first KB, this one, this KB is K capital B, and this KB is K little b. And so there's a lot of confusion. Even on the internet, I looked on the internet, on certain people's website, even they have it confused. When you have a K with a little b, that's kilobits. K small b is kilobits. K big B is kilobytes. Kilobits, kilo in that case means just what you think. Kilo means 1,000. So a kilobit is 1,000 bits, 1,000 zeros or 1,000 ones or a combination of the two, but it's 1,000. When you mean kilobytes, when we say kilobytes, it doesn't mean 1,000 anymore. The reason it doesn't is, and I'll show you this when we get to number systems, we humans, we use a base 10 number system because we have 10 fingers, 10 digits, 10 toes. Computers only have 2 fingers. And what do you mean by that? Well, computers are based on switches, and the switch can either be in one state or another, so it has like 2 fingers, 2s. And so there's a system of numbers, a number system that deal with 2s, and that's called the bi means 2. The binary number system fits right into what we're doing in digital electronics. And so with 1,000 in that binary number system, or I shouldn't say 1,000, a kilo in that binary number system is not 1,000 as it is in our number system, our base 10 number system, it's 1,024. So if on an exam or quiz, I say, all right, you have 2 kilobytes. 2 kilobytes, how many bytes is that? You can't say 2,000. It's going to be 2 times 1024. If I say you have 2 kilobytes, you have 2 kilobytes, how many bits is that? Not bytes, how many bits? If I ask for the number of bytes, it's going to be 2 times 1024, because 1 kilobyte is 1024 bytes. So how many bytes is 2 times 1024? But if I want to know how many individual bits I have in 2 kilobytes, I'm going to take 2 times 1024. That'll give me the number of bytes. And then I got to take that, the bytes, and convert that to bits. Well, 1 byte is 8 bits. So I have to take 2 times 1024, and then I got to multiply that by 8 bits in the byte, and you got your answer. So at some point, I think I show an example of sizing memory. So here's what you need to know. I want to be clear. You need to know that a bit is a 1 or a 0. You need to know that a byte is a group of 8 bits. Now the next term, word, the word. It says here on the PowerPoint that a word can be 1, 2, or 4 bytes wide. And that's actually, a word can be any size, as long as there's some power of 2. A word is machine dependent. A word is machine dependent. And what does that mean? Well, let's say you're designing a computer, you're designing a PLC, you're designing a cell phone, you're designing any kind of digital device. At the point of design, you can make your word size any size you want, as long as there's a power of 2. You can make a word 1 bit wide, you can make a word 2 bit wide. 3 is not a power of 2. You can't raise 2 to some power and get 3. But 4, 2 to the second is 4. So I can have a 4-bit wide word. The wider the word, the more information you can move around in a given time if you're a microprocessor. So what you want to know is a bit has a specific definition. It's a single binary digit. A byte has a specific definition. It's 8 bits. But a word is machine dependent. It depends on whose machine you pick up. If you're Microsoft, you can make a word size 64 bits. If you're Dell, you can make a word size 128 bits. As long as it's a power of 2, you can make the word size any size you want. Well, you might say to yourself, well, hell, why don't we get a really big word size? We can move all that data around in big scoops, because we usually try to move words of data. Well, there's always a trade-off in everything, guys. The bigger the word, the more complicated the circuitry. So there's always a trade-off when you're designing these systems. But I don't want to get lost in that. I want you to know the definition. A bit, a 1 or a 0, a byte is 8 bits. A word is machine dependent. It can be any size, as long as that number is a power of 2. Now, having said that, in this class for us, a word size is going to be 16 bits or 2 bytes. So what I want you to write down on your slide, if you have the printout, I want you to write the definition for bit, write the definition for byte. But when you write the definition of a word, write down that it's machine dependent. What does that mean to be machine dependent? Well, they can choose the word size at the point of manufacture or design. When they design it, they decide the word size. For us in here, a word size for us is going to be 2 bytes or 16 bits. Why? Well, it turns out that when you store those zeros and ones, remember in the last class I showed you that virtual logical structure I called a input-output image table? Well, what that really is, in memory, you have a group of registers. Now, we talked about in week 1 shift registers. You can shift data in serially and shift it out serially. That's serial in, serial out. Remember that discussion? We talked about data transfer. You can shift bits into a register in single file. Serial in, you can get them all out at once. That's serial in, parallel out. Or you can shift them in parallel and shift them out in parallel. That's parallel in, parallel out. So there's advantages and disadvantages to all of those I just described. But a register, the essence of it, a register is just a physical device. It's not something that exists in memory. It's an actual device. You can go to the electronics store and say, hey, I want to buy a register. And that register will be designed and it'll be a certain size. You can buy, as long as there's a power of 2, you can buy a 16-bit register. And what you can do with that is put it on your printed circuit board. If you know how to hook stuff up, electrical stuff, you can actually store 1s and 0s in that register. So for us in here, a register is going, a word is going to be 16 bits. And the reason is The screw terminals that we use to connect to the input module or output module, on your simulation software, there's 16 of them. Remember, in digital, we start counting with 0. So each one of those screw terminals, if I had the physical PLC in here right now, and I pointed to the input module, there's a door on the input module that I can open up, and you will see 16 screws labeled 0 through 15, and above or below each screw, you'll see 16 LEDs. And you can take like a normally open push button and connect to one of those terminals. And if you have power hooked up the right way, when you press that push button, you send a signal into the input module, and also that LED will light up so that you can actually physically see that, hey, there's a signal going into it. The point I'm trying to get at, though, is however many screw terminals you have on your input or output module directly affects the size of your register, or I should probably the other way. The register size, it's going to take those zeros and ones from those screw terminals. So if I have 16 screw terminals for 16 connection points, then I need 16 spaces in my register to store those ones and zeros. So that's why in this class, even though we understand a word is machine dependent, for us in this class, a word is going to be 16 bits, because on your simulation software, you'll see when you look at your input or output module, there's going to be 16 connection points. So for us, one word is 16 bits or 2 bytes. And so I think I talked about that, but I didn't go into as much detail as I just did. And then the other thing that was important, right here, volatile versus non-volatile. We already mentioned that. If it's volatile, that refers to memory. If it's volatile, that means that memory is going to lose its content if you remove power. If it's non-volatile, it's going to retain the contact, whether there's power or not. Typically, RAM is volatile, ROM is non-volatile. When you work and interact with memory, you are interacting with RAM and not ROM. ROM is programmed at the factory. And again, the most important reason we have ROM or we use ROM is just to tell the computer, the phone, whatever digital device we're talking about, how to load the software, how to pull it off the hard drive out of storage and put it in the RAM, into memory. So you want to know the difference between those two. And these other points I kind of skipped over. Well, you know, we mentioned, we'll talk about addressing, but if you think about the cells, think about a register. Even though it's a physical device, think about it as being like one row of an Excel spreadsheet. And you maybe have 16 cells in the row, and you can put ones or zeros in there. And those ones or zeros, you can map each one of those cells to a particular screw terminal on the input module, and then you can connect the switch to that. And if the switch is open or closed, it'll put a 1 or a 0 in that particular cell that it's mapped to, depending on if the switch is open or closed. Well, how do we map a screw terminal to one of the cells in the register? Well, you do that using an address. And I gave a kind of a really basic example of addressing. Every PLC manufacturer has a different addressing schema, but they all work like this, from the wide down to the narrow. So last class I gave an example. If I want to, I'll just use me as an example. I was going to use an actual student, but so I'm Ron Singleton. So I live on planet Earth. I live on the continent of North America. I live in the country of United States of America. I live in the states. I'm going more and more narrow. The state of Ohio, the Hamilton County, the city of Cincinnati. I live in Bond Hill. I live in on Reading Road. My address is 5024. I probably shouldn't say this because this is going on the internet. But anyway, my address is 5024 Reading Road, and I live in apartment number 2. And now you're in my apartment. I've given you that address. It's gotten more and more specific. I can even tell you which room of the house, which room of my apartment I'm in. Addressing works like that because, as I mentioned in the last class, the smallest chunk of data you can address in a typical digital device like a PC or a cell phone, the smallest hunk of information you can get that you have access to is 1 byte. When you press the letter K or A or Z on your keyboard, on your cell phone, on anything, it's stored as a group of zeros and ones, and there's 8 of them. But when you interact with the PLC, it's different. A PLC is actually a bit-oriented device, which means it can actually change individual bits, and that's where PLCs differ from regular digital devices. And so that's kind of what this is saying right here when it talks about memory utilization, one location per coil or contact. A relay contact can be open or closed. And so what we're going to do is represent that relay in memory. You know we can do that already, right? Because we talked about virtual devices, and you know there's three that we talked about. There's a relay coil, there's a timer, and there's a counter. So a relay coil can be on or off, or the contact can be open or closed. Any device that can be talked about in one state or another can be represented with a 0 or 1. And so we can have a software relay by just having a space in the register that if I have a 0 in there, that means my contact is open. I put a 1 in that particular cell, that means my contact is closed. And so there's one bit location to represent each relay contact or each relay coil, is what that means. So this is a good picture also to mark the sections of memory. Now, let me say this. Strictly speaking, you have memory and you have storage. So memory is RAM. When we talk about memory, 99 times out of 100, you mean RAM, random access memory. But then there's storage. That's like your hard drive on your computer. So if you're using your computer, when you bring Microsoft Word up and you're typing the letter, you're using that application that's been pulled from your hard drive and loaded in the RAM. So you're actually interacting with RAM through the OS. You're interacting with RAM. Well, if you want to save that letter to use it later on, now you're going to save it. When you save it, it's not saved in memory. It's going to be saved on your hard drive. It's going to be saved on your thumb drive. It's going to be saved on some medium that we call long-term storage. So there's really a difference between memory and storage. However, when you deal with PLCs, we just kind of fudge it, and we can just think of memory and storage as being one of the same. If for some reason we have to talk about the differences between them, we'll bring it up. But for most purposes, it's okay to think about your hard drive and memory as being kind of the same thing. Okay? So keep that in mind. So with that said, this diagram is good for you to mark because it talks about the sections of memory and the main three sections. If I ask about this on a quiz or exam, you have storage. So the storage is just whatever we're going to keep long term. I want to be able to turn my PLC off and turn it back on. It's in storage. It's in that part of the memory. And then there's the input image table. And remember, I mentioned to you that when in textbooks they call the input image table, but when you buy a PLC, no matter whose PLC you buy, they're going to call it a data table. So I don't know if you had a chance to download the free version of the software yet, but if you looked at that and played around with it, you'll see an icon with I think it's a hammer and a wrench or something on it. You click on that. That's your data table. That's your input-output image table, and you'll interact with that as we get more into our programming when we get to the labs. So the three sections of memory are storage, input image table, and the output image table. Storage is for keeping stuff long term. The input image table stores the state of the input devices, whether the switches are open or closed or whatever. It's going to store the state. If a switch is open in a particular bit position, it's going to store 0. If it's closed, it's going to store 1. And the output image table does the same thing. It's going to have a 0 or 1 depending on what logic you write. It's going to put a 1 or 0 in a particular bit position of the output image table or output data table. And then depending on how you wrote your program, if there's a 1 on that particular output, a cell in the output image table, it's going to turn that output on. If there's a 0, it's going to turn it off. And so to get a big picture of that, just to kind of close things out, I showed this diagram. So this kind of pulls everything together. And if you understand this, then you have a good idea of kind of how the PLC works. So it really, when I first started teaching this back in, I think, 1999, I was like, man, why don't we just jump right into the programming? But it really, really does help to understand how this hardware works. Now, you guys typically will not have to set this stuff up. If you get a job working with PLCs, they have a plant electrician or somebody trained to hook up the sensors and all of that. That you probably won't do, but there's no reason why you can't write a program to control some kind of industrial process, especially if you're ME or MET. And so it helps to understand how the hardware is interacting with the software and all of that. So on this slide right here, everything on the left side of this line right here, everything on the left side, everything over here, that's all hardware. And everything over here on the right side, that's the side of the memory. That's virtual stuff. That input image table is not real. It's a virtual logical structure. It's in memory. And so what we have here is we have that input module that I keep referring to. And these are the doors right here. Here's a door, here's a door. These are those doors you can open up. And if you open it up, what you see is I didn't hear what he said, but you see screw terminals connected there, right? And so this switch right here is closed. And so this is mapped to this particular bit right here. And so since it's closed, there's a 1 in that table. And then right here, this switch is open. Come on. This switch is open. And this switch terminal is mapped to this bit position. And so there's a 0 there. Now that constantly changes depending on if the switch opens or closes. And so your program's looking at those, and depending on how you wrote your logic, you're either going to have a output or you're not going to have an output. And so this hardware is mapped to these bit positions over here in the image table through the address. And it's the same thing with the output image table. But here, if your particular program say, all right, we're gonna put a 1 right here, because that particular part of your program turns out to be true. So this is a 1, then whatever's mapped to that output is going to be turned on. If there's a 0, whatever mapped is going to be turned off. Okay, so I went through that kind of quickly in the last class. So I just figured I better go back through that, because this is a short PowerPoint, but there's a lot of good stuff packed into that you need to understand. So, whew, boy, that's a lot of talking. So that's not the one I want to do today. That's the one I kind of ran through real fast in the last class. So I wanted to go back and just kind of clean that up a little bit. But now, let me ask you, does anybody have any questions on anything I just talked about with this PowerPoint on the CPU? Any questions or comments before I go on?
So the memory on the hard drive, is that ROM?
Okay. Well, I saw you. Let me see what you guys are chatting. Let me see if you guys are talking about me. Let me see. So, all right. Sam Baker laughing. Let's see. Yes. Oh, okay. So you're gonna show up in my house when I should have beer. All right. You know, it's funny. This was years ago. I was kind of playing around with the quiz with the class. And I wanted to give an extra credit quiz, just to get free points, because I just felt good that day. So I asked the class. I said, take out a sheet of paper. This is a quiz. What's the major ingredient in orange juice? And I'm going to write orange. It's supposed to be 3 points. They wrote vodka, and I thought to myself, well, I guess college students, that would be the major ingredients in orange juice. Ha 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 ha. All right. Anyway, bad joke. All right, let me.
Hey, Professor.
All right, let's go to the PowerPoint for today. So, wait a minute. What was that again about memory? You guys are.
So, is the memory hard drive, is that ROM or RAM?
Who said something about memory? Can you guys open your microphone? I'm not tech savvy like you guys. Somebody asked something about memory. Could you have a microphone?
Yeah, I'm trying to.
Or was that a joke?
Ah.
I'm using my mic. Aaron, how come I can't hear you?
I don't know.
Wait a minute, hold on a second. If he's using his mic, I might have an issue. Say something, Aaron.
Hey, hey.
I wonder if I'm muted. Wait a minute, hold on a second.
Well, now that he can't hear us, it's time to talk about it.
Somebody say something.
Can you hear us?
Video mute, audio mute. Oh, I don't know why it's on. Let me check one more thing.
So what kind of keg are we getting?
That depends. Do we really want to go hard or be like cost conservative?
Do they make kegs of White Claw?
All right, I don't know what's going on. I see the microphone thing. I really hate that because I don't know if you guys have questions or not. I tell you what, technology is fine as long as it works, and then they keep moving me around. I have to keep moving. I'm playing rotating classroom. So I'll have to slow down and look at your texts. I didn't realize you guys couldn't talk to me, and I'll have to figure out why you can't talk to me later on. I don't know what's going on here, but let me go to the other PowerPoint, and if you have a question, I'll try to watch. Just send me a message. And now somebody asked about memory. What was it? Is memory on the hard drive wrong? Let me go over that again. I really hate that you guys can't talk to me. I really, really do hate that. So memory and the hard drive are really two different things. You have memory and you have storage. So what you have is, I don't know if you guys text me. If you didn't, go ahead and do that. 513-494-6162. But what you have on your PC, here's your PC. You got your PC. Let me get a clean marker. Here's your computer. PC. And then you have your hard drive. So that's long term. So when you hit the save button on any of your applications, any of them, you're saving it to here, not memory. Memory is actually inside of the PC. Inside of that, typically you have your microprocessor in there. And then you have this big chunk of memory here, and it's always RAM. So really, storage and memory are two different things. When you're talking storage, you're talking your hard drive or your thumb drive or something like that. When you're talking as an actual chip, separate from storage, separate from your hard drive, usually placed in close proximity to the microprocessor. And when we talked about data transfer, typically this data transfer is parallel data transfer because you got to be able to read to and write from the memory really, really fast if you're the microprocessor. I don't know what processors today are that, but when I had my first computer back in 1998, my clock speed was 500 megahertz. They're in the gigahertz now, so they're like super fast, right? Maybe even faster than that. So my RAM here is actually separate than storage. RAM, memory, hard drive, storage. This is short term, it's volatile. Your hard drive is long term. Doesn't matter if power is on or off. Whatever you put on your hard drive is going to stay there. What I was saying though, for the purposes of this class, we're going to assume that two are the same. They're part of each other. So we're just going to kind of say, all right, memory. So right there, that you can think that's RAM plus your hard drive. We're not going to distinguish between the two. So that's one part of memory, the RAM plus the hard drive. And then you also have these two tables in there. One of these is the input in this image table, and the other is the output image table. That's not really the way it is. That's the way we're going to think about it for this class, just to make what we're doing and what we're talking about a little easier. And you'll see, right now I'm giving you pieces of a puzzle, and it'll come together soon. You just kind of got to follow what I'm saying. So strictly speaking, memory and storage are different. But for the purposes of this class, when I say memory, I'm talking about RAM and the hard drive. We're not going to distinguish between the two. I don't know who asked that question, but that was a good one. All right, let me move on because I don't want, oh wow, I'm almost already out of time. Damn it. I'm sorry guys, I forgot. And I gotta be careful because I'm putting this stuff on YouTube and I don't want to be kicked off of YouTube for using foul language. But that is not I don't even know if that's a foul language. Let me see how much of this I can get through, guys. I'm going to try to go through this. It's not really too bad. I may have to, I'll go back through it again on next time if we have to. Uh-oh. Well, I think I made a mistake. I didn't let me see if I can upload that file. I uploaded the wrong file. Yeah, I might have to put some bleeps in my YouTube. All right, we'll go through this. I'll probably run out of time. I'll clean it up on Monday, and then we'll talk about number systems. Wait a minute. What am I? Okay, all right, I got it. All right, so I kind of got off track, but I don't mind getting off track. You guys asked really, really good questions, and I think I don't mind getting off track as long as we're learning something. And I really, really like it when you learn a concept and you can apply it to something you already have. Like, okay, now the guy asked about clocking computers, and somebody else, when they dealt with relays, they remember hooking up lights on their car. I like that kind of stuff. That's really, you can listen to me talk all day, but to be honest with you, learning is in doing. You got to do something. You can't just listen. It's got to be some kind of action. And some of the stuff you guys have already done, and you say, I get these messages and say, hey, this makes a lot more sense now. So we'll run out of time, but I'll get through as much of this as I can. This one, we're still talking about input-output modules. There's two types of input-output modules you can have. You can have a discrete module, or you can have an analog module. Discrete and analog. So I want to talk about the differences between the two. So what is discrete I/O? Discrete I/O is any kind of device or any kind of signal that's in one state or another. Anything that's what we call bit oriented. So as I mentioned before, a switch can be open or closed. A motor can be on or off. A fan can be running, or anything that can be in one state or another. You can use a switch or a button that's either on or off. That's what we mean by discrete. And so those type of input modules, that type of I/O, is called discrete I/O. And so it mentions that discrete I/O is, said, input devices on-off nature. Switches, buttons, levers. There's a lot of different kind of input devices that are either on or off, or that's in one state or another. It's going to switch outputs off or on. So either you want the light off or on. It's either going to be off or on, not in between. What do you mean by in between? Well, you know, maybe I have a light bulb. I don't want it to turn on or off. I want it to turn on and then fade up to a certain brightness. And that's a different kind of output module. I can't do that. The discrete module only deals in things that are two-state devices. So a light bulb is either on or off, a switch is open or closed. That's a candidate for this kind of input module. So we call that bit-oriented, where we can use one bit to represent the state of something. I can use a bit to represent whether a switch is open or closed. I can use a single bit to represent a light bulb being on or off. Light bulb is on, we say that's a 1. Light bulb is off, is a 0. So anything that's like that, that's bit-oriented, I'm going to use what we call discrete I/O. So what are some of the tasks of the input module? The tasks of the input module. to sense when a signal is received from a switch or sensor. That's the most important thing. It's going to tell the microprocessor there's a switch out there and that switch is open or closed, or there's a transducer out there, and we'll talk about what that is here, if not today, then next time. There's going to be a digital code that microprocessor has to interact with and put in the memory. So it's got to sense the presence or absence of a voltage or current. Once it receives that signal, it's got to convert that signal to the correct voltage for the PLC. And so there's circuitry in the PLC, in the input module, that can do that. Maybe your switch puts out 5 volts, but the input module might want 3 volts. There'll be circuitry in there to reduce the voltage to the proper level. To isolate the PLC from current voltage fluctuations, that happens a lot in factories and where there's heavy motors starting and stopping. If you've ever been in your house, maybe watching TV, lights are on, and somebody starts up a machine, a vacuum cleaner, a heavy machine, and the lights flicker for just a second, surge currents cause that. And typically, that's not an issue, it's not a problem at all. But with a digital device, it could actually make it skip a beat. It could actually cause a 1 to be in a place where there needs to be a 0, or vice versa. It can cause issues and problems. And so PLCs have circuitry built in to help with what we call noise. And then to identify to the processor which sensor or switch originated the signal. And that has more to do with addressing. And so we talked a little bit about addressing. Now, this next slide, I want you guys to mark it. I'll ask a question about this at some point. When you get an output module, there's 3 classifications of output modules: transistor, triac, and relay. Transistor, triac, and relay. So I think on the quiz it's something like name 3 types of output devices. I forget how I asked the questions, but this is the slide I'm referring to. Transistors, triacs, and relays. The first 2, the transistor and the triac, those are solid state devices. Remember, the term solid state means no moving parts. The difference is transistors are for control of DC devices, and the triac is for control of AC devices, but both the transistor and the triac are solid state devices. Relay, well, you can control either AC or DC with relays, and relays are not solid state. Relays are actually electromechanical switches, physical switches. And so output module classification, mark this slide, and I will talk about this at some point. I'll ask about it. Now I'm going to switch to the camera for this next one. You can read this if you want to, but I can show you real simple what this is. So let me switch to the camera. And I'm sorry you guys can't talk to me, but in electrical and electronics, there's something called a source or a sink. A source or a sink, and all it is whether something's giving out current or whether something is taking in current. And let me show you the difference between the 2, and you'll see it. Say you're controlling some kind of device. Well, one way to hook it up is like this. You got your output module. Here's your PLC output module. And connected to the screw terminal, you got some kind of device. Maybe you got a motor. So here's my, I don't like this one. Here's my motor. And if you don't know, this symbol is just short for ground. So in this scenario, current's going to flow like this. It's going to flow out of the PLC into the motor. I'm assuming that's a small motor and this thing can put out enough current. So this thing is giving current to something. It's sourcing current. It's the source of current. This is a source. Well, maybe your PLC is not designed that way. Maybe it's designed to be hooked up like this. My PLC output module. Maybe I got to take the motor. I got to hook the motor to power. So right here, I gotta have power, voltage, and then I connect this to the screw terminal of the PLC. So now power is flowing this way. It's flowing into the PLC like that. It's sinking current. So imagine water. The faucet would be the source of water or current. That's like this one. And the drain would be, I'm sinking current into the PLC. So this is a source of current, and this is a sink for current. It matters when you buy a PLC and you're setting it up. It matters because if your PLC, and most of them probably source current, I don't know, but it matters if your device sources current, you got to hook up your outputs like this. If it sinks current, you got to hook it up like that. You got to know that, and it'll be clear from your spec sheets or whatever you get, whatever kind of docs you get for your PLC. So you really do want to know the difference between a source or sink, and it's pretty simple. Got about 2 minutes, so let me see. You know what? This is actually a good place to stop because the next couple slides gets into analog, and I don't want to rush through it. I kind of hate to stop it now because now what happens is I'll title the next video. I think we talk about number systems next week. So I'll title it number systems, but then you'll have some of the hardware stuff on it. But I guess we can't help that. It's actually a good place to stop. So guys, let me ask first, does anybody have any questions? I'll look at my screen now. Anybody have any questions over anything I talked about today? Any questions? I don't know what is wrong with my audio. I'm so upset you guys can't talk to me. If you think of anything, send me a text. Remember, when I get the quiz up, I'll send you an announcement out. But I'm going to leave it up instead of making it do Sunday night like I usually do. Since I'm putting it up late, I'll make it in the Monday. That way you'll have time to take it. 10 minutes. Just remember to look at the week 1 objectives and make sure you're familiar with those kind of things. And look at that practice problem we did with the waveforms and the frequency and period and bit time. And I think if you look at that, you should be in good shape. So guys, have a great have a great weekend. And I'll put up the videos for this week at some point. If you missed anything, go back and review those. And if you have any questions, comments, concerns, send me a text and I'll address it as soon as I can. Thank you, and I'll see you on Monday. Oh, wait a minute. Somebody said, can you explain input, output sections of memory? So, yeah, I was just, we talked about input, output. So what that is you have memory. This is the way we're going to think about memory and the PLC. Memory and the PLC. And I put it in PLC only because it's not really this way. Like for PCs or your cell phone, you don't think about it this way. But for purposes of the PLC, when we think memory, we're going to think of memory as being structured like this. Over here is storage. And over there in storage, what's going to be in this side, the biggest thing that you have to concern yourself with, that's going to be where you keep your program. Your program is stored here. So you're going to write a program, it's going to be stored in there. The OS is stored here, the operating system. And then there's some other housekeeping stuff that, we don't have access to, that's kind of behind the scenes that your computer's doing or whatever. The main thing is that anything that needs to be held onto long term is here in storage. So when we think of memory, we'll think about it as there's a part of it that we call storage, and then there's another part of it and I'm going to write that down here. This is that input image table that we talked about. And then there's another one of these tables. That's the output image table that we talked about. And all this is a group of registers that stores zeros and ones. And all this is the same thing. It's a group of registers that store zeros and ones. But what you want to remember is this input image table, those zeros and ones are representing switches hooked to the input module that are either open or closed. It's storing the state of those switches in the input image table. The output image table is storing ones or zeros that it got from the program you wrote. So it's going to work like this. Let's say over here, I'm just kind of jumping ahead right now. Let's say right here, I don't know where to draw it. Let's say right here, that's your input module. And you got two switches. So you got maybe you got a normally open push button, and maybe you got a regular single pole, single throw switch hooked to the input module of your PLC. So you got this switch, you got that button and that switch. I want to write a program that if that button is pushed and at the same time, not or, but and. If that button is pushed and that switch is closed, I want to turn on a light. So over here, you have another module. This is the output module. And hooked to that screw terminal, you got a light. And we'll say that this source is current, so I'm going to do it like that. So in here, actually in here, in memory, if you close that button right there, then there's these registers in here, those cells I was telling you about. This is like a grid. And what you got to do is you got to map that screw terminal to one of these positions in the register, one of those cells. You got to map that screw terminal to another one. The way you do that is using the address. So what you'll do in your PLC software, what you'll do is your program is basically going to look like this. The instruction you're going to use like this. Now, you know from when we talked before, if I want to make an AND circuit using switches, I do this. I just got two switches, A and B, in series, and both switch A and B have to be closed in order for me to have current over here. If I do it the other way, like this, and this is A and that's B, well, that's OR. This is AND logic. This is OR logic. Well, what you're going to do, not with physical switches, but in software, you're going to do the same thing. But what we're going to use, instead of using switches and buttons and all the different things that we can hook in series and parallel, we're going to use one instruction to represent this thing, or really any input. And it looks like this. It looks like this. That's a normally open relay contact. And that's a normally closed relay contact. So here's what I can do. Instead of wiring up physical switches, I can just drag this literally from my software instruction set. I'm going to just drag this symbol onto my screen. I can drag another one onto my screen. And if I want AND logic, I just put the two instructions in series like that. And then there's an address that I can, let's say this is A and this B. I'm going to represent the address with A and B. So there's an address. There's some stuff I type in to connect this with that and this with that. So I'm going to say this is the address A, this is the address B. Now this thing knows to look at that switch, and this thing knows it's connected to that button, or this button and that switch. Well, I got the output over here, the light. The way you're going to show any output is with that. This is the actual symbols we'll use. This could represent anything, a light bulb, whatever. It represents whatever you want to control. And so just like when you close A and B if I have a light bulb over here, I can light it up. What this thing is going to do is, if you close A, then whatever cell A is mapped to is going to put a 1 there. And if you close B, whatever cell B is mapped to, it's going to put a 1 there. If this opens back up, it's going to change that to a 0. But let's say this is pushed down, so there's a 1 here. And that's closed, so there's a 1 here. Well, this thing's going to look here. If it sees a 1 there, it's true. And then this is going to look right here. If it sees a 1 there, it's true. And since these are hooked in a series, that's AND logic. If I have two inputs that are true or AND logic, that makes the output true. So that means over here in the output image table, there'll be a 1. This will be mapped to a certain position in the output image table. There's a 1 there. And when there's a 1 there, whatever physical screw terminal that's mapped to, it's going to turn that on. Now, I said a whole lot. So hopefully you understood a little bit. Maybe you understood everything. I don't know. But what we'll do is we'll dig into this slowly, and you'll see it. It's not that bad at all. But a direct answer to your question, we think that we've got memory, and I want you to think of memory. Just let me simplify this real fast, and I know you got to go. So all I want is you to think of memory like this. You got this box that we're calling memory, and then you got 3 sections in memory. One section is storage. One is the input image table. I'm just going to say input table. I better say image table. And the other is the output image table. And then we'll just kind of leave it at that. Now, I'll come back to this, and I think this will become more clear as we dig deeper into this. So I hope I answered your question. I don't know if I did or not. I kind of can get too detailed sometimes. So, guys, anybody else? Okay, thank you. And then Will says, for homework, can we just type the answers in Word? And yeah, you can do that. Yeah, I think you can upload it as a what was that homework assignment? Yeah, that's the one you have to answer the questions. Yeah, you can type it in the Word and upload it as a PDF. That works. I think that's what most people do anyway. So, well, guys, man, you guys ask really good questions. I love it. It makes teaching this a pleasure. Have a good weekend, guys. I'll see you later. See you on Monday.